Good afternoon. I invite you for our next lecture. And today's lecture is about x86 architecture. So it is about the architecture which most of you are using in your laptops and personal computers and so on. And we will start with some short overview of the history. And then we focus mainly on those aspects which are important for your homework number 4. So we will skip a lot of other things. I have even a recording, much longer recording about the full history of the processor and so on, but we would not fit into the time. So basically, if you have some architecture, then what is important to know, what is the user visible instruction set architecture, and what is the weight of the registers and so on, and which instructions are supported and so on. And then there is the internal microarchitecture, which is which can be different. So for example, even 32-bit x86 has used internally 64-bit or even 128-bit wide buses, but was externally only 32-bit. On the other hand, you can have architectures which are, for example, internally 32-bit, or which provide 32-bit instruction set, but has only a 16-bit buses and so on. So it is one side is that implementation, and in theory, if you program the program according to some standard of that architecture, then it should run on all different implementations. But on some of them, some combination of instruction will be processed quicker. On some others, it will be slower. So it can depend. Anyway, so the important is what data types are available in the memory and how you can access it and address it and what are the registers and so on. And then a number of the registers which is important even for the compilers, because if you have more registers available, then there is not so often necessary to switch between the memory, for example, stack, that automatic variables location, and the registers and so on. So it can be a better if you have more registers. And then another parameter which is usually in the documentation and so on is clock frequency. It usually, when you have a higher clock frequency, then the throughput is usually higher, but it is not necessarily so, because, for example, a Pentium 4 has been planned for very high frequencies, up to 4 or 5 gigahertz, but was relatively slow. So it depends how many instructions per single clock cycle you are able to process and so on. And our program manipulates with registers, requests some arithmetic logic operations, and usually it has some instruction pointer and so on. If you look at the x86 architecture, then its initial versions can be traced to 1970, where the Intel started with 4-bit 4004 processor. Then it has been extended to 8-bit, then to 8-bit with some additional features. And then a time came when they decided that they need to switch to something more powerful. So they switched to 16-bit core. So our today x86 architecture, the X here means that it can be one of all those variants, is in the fact extension of 16-bit architecture, which initially allow only a 20-bit physical address space, so basically only 1 megabyte of the memory can be addressed, and it has mostly 8 16-bit registers. And it was relatively slow. Then the architecture has been extended to allow 16 megabytes of the physical address space, but still with 16-bit wide registers, which is quite narrow. And it added a protected mode, which allowed to protect the processes and some users and system and so on. But it was quite complicated system with descriptors, selectors, and so on, which was something okay, a little strange, because other architectures has added paging at that time. And Intel later added the paging as well, and extended the architectures to real 32-bit architecture with 32-bit wide registers and address bus. And at that time, if you want to work with floating point, you have to add the additional chip, so-called coprocessor. But on 486, the floating point unit has been added to the on the main processor chip. Then at the time of Pentium, initial superscalar extension has been available, which allow in optimum situation to execute 2 instructions in parallel, 2 integer instruction, or 1 integer instruction and 1 floating point, because floating point has a separate pipeline. Then the naming with that 5, 6, and so on has stopped to be used in the future versions, but we have there the Pentium Pro Professional with paging extension, which allows physical address extension, which allows to work even with more than 4 gigabytes of the memory. It extended it to 64 gigabytes for the servers and so on. But one process physical virtual address space was limited still to 4 gigabytes. Then Intel have found that basically the architecture is problematic, and decided that they try to do a complete new design of the architecture, which has been called the Itanium. It was 64-bit, it has a lot of registers, it has a quite wide physical address, and okay, and it was over-engineered. So basically, it has a lot of problems, and even that the second variant of this very long instruction word system has been quite capable for scientific computation, for example, global climate computation and so on. Then due to the incompatibility with the binary code for the Windows applications and so on, it didn't fly at the end. And at that time, AMD, company who knows that they do not get the license for that Itanium instruction set, they decide that they try to extend the original 386 design to 64-bit. And this extension has been quite useful. What is interesting that when the AMD need to design a 64-bit processor, that they started on the Unix workstations with the design, and some maybe even Windows stuff. But when they have the first prototypes of the 64-bit AMD, they have switched to the Linux, which has been ported by the team of SUSE company, which has the main lab located in the Prague. So basically, they have developed the first 64-bit version of AMD and use it to can enhance the design and correct the design and so on. So it is quite interesting. And it has 40-bit physical address capabilities. Today, most of the x86-based system has 48 bits of the virtual address, and for physical address, usually something like 44 and so on. Okay, and Intel found that Itanium basically is unusable for the future, so at the end they switched to the same 64-bit extension as AMD, and they started with some, they call it EMT 64 or 32 technology, and later they have 64-bit wide registers. Number of registers is extended from 8, the main registers, to 16, and even today there is extension which allows to use even the 32 integer registers on the Intel on some server products, which is quite interesting. And later there has been added the multimedia extension for fast processing of video, audio, 3D graphics in the games and so on. In the fact, internally, all those later versions of the Intel processors has switched to the RISC architecture. So even that externally you still use those instructions which has been designed in 80s and are quite complex and problematic to execute, then they have switched internally to RISC architecture. So internally, at the time when the instructions are fetched, they are decoded to the RISC micro operations, which are processed later according similar rules as on the RISC systems. Okay, there is little more detailed list, but you can go even deeper to the detailed list. And if you look at that 64-bit variant of the x86, then it holds all that heritage. So you can see this AL and AH are heritage of the 8080. This AX 16-bit access to the registers is 8086. Then 32-bit registers are 386, and then this is that AMD 64 extension. There are interesting rules that if you replace and address only that lower parts of the registers, then it doesn't modify this of the register. So basically, you can modify only part of the register. Later, of those 32-bit registers, you can modify only lower part or the whole register. But those keeping of previous value in the upper bits of the registers has proved to be big problem for the superscalar execution, because it adds additional dependency on the value which is usually not reused from the rest of the register. So for this reason, there has been a problem with the optimization and the speed. So for this reason, when the AMD extended the processor to 64-bit, they decide that if you store the value only to the lower 32 bits, then the rest is 0 extended. So basically that whole RAX 64-bit register is rewritten for each of those 32-bit operations. Those are those 8 registers or 16 registers which are used for the integer arithmetic, and then we need some control registers, and the one which is most important is the current instruction pointer, IP, and you see this is 16-bit, this one is 32-bit and 64-bit instruction pointer register notation. And then we need some processor status and control register which allows to disable interrupts and so on. We have seen those control status register for the RISC-V, that's it. Then this one is the main one which has been there from the beginning. And in this case, this architecture, and maybe it is even important, is different in that aspect that the conditional branches are not done directly in the one instruction with a compare of the values in the registers, but they are done according to the result in the so-called conditional code part of the flux register. So basically each arithmetic logic, or almost each arithmetic logic operation sets those bits which inform if there was unsigned overflow or carry, what is the parity of the result, if the result is 0, if the sign is negative or positive, if there is arithmetic overflow, and there is some additional flag which allows to compute in binary code decimal values. And this part of the flag registers is accessible to the user and can be stored, restored, modified, and so on. Then there is another part where is the bit which allows to mask the interrupt, requests that the interrupt or exception is placed after one instruction execution. So this way, if you return to the user code with trap flag set, then basically you can step instruction by instruction through the user code, because after each step the exception is received, it can be routed to the debugger and so on. Then there is I/O privilege level for access of I/O ports. It is history in the fact. And then in the system part, there are flags which allows to do or helps to do a virtual 16-bit execution of the DOS application in the 32-bit system and so on. So it is a lot of history. Anyway, if we go to the flux, then in the 64-bit mode, we use only 2 privilege modes. Originally there has been a 4, but on the 64-bit we have only the CPL current privilege level system mode 0, which is for the privileged application privileged operating system operations and so on. At this mode you can access whole hardware I/O ports, and you can manipulate it, the paging state and so on. Then there is CPL3, which is user mode, which cannot modify the page tables and access the peripherals and so on. So this one is with the limited access and privileges. In the fact, there are many more modes as the processor starts, because it initially starts in old 16-bit real mode, then switch to the 32-bit mode, then you need to manage switch to the 64-bit mode, so it is quite complex. Anyway, at the moment when we get to that protected modes, we have some privileged operations which are not allowed to the user, because they can manipulate with whole system or the given core state. So basically, for example, disable interrupts, modify a whole flux, which allows even to modify some that priority to access peripherals and so on. You can access MMU registers, switch the page directory register in the fact and so on. So this is the privilege operation. And there is some option how the input-output operation for that area, special area of the input-output ports can be accessed even from unprivileged code, but that it can be granted. But in 64-bit mode, it is much more limited than in 32-bit. And anyway, today's suggestion is not to map the peripherals into the original I/O space, but map them in the standard memory regions and so on. But anyway, processor starts in that DOS mode, compatible mode at the start. Then we need to do the complex sequence to switch to 64-bit mode, and we appear in that system mode at the start. So you can set up page tables and so on, and then there is done a switch to the user application. So basically you set up some part of the memory, switch to the user application through the pop or return from interrupt instruction, and the user cannot manipulate with that critical state of the processor. When user wants to invoke some system service, then it is possible only by the interrupt. Same for the external asynchronous interrupt. Basically, when interrupt arrives, and if it is enabled, then it switches the execution to the system mode, or that CPL0, and commands the processor to continue from some specific location, from some interrupt service routine for a given interrupt. So it is how we switch to the operating system. Originally, it was possible only through the to invoke the services only through the int operation, which invoke a synchronous interrupt with a given number. 0x80 was a system call for the Linux operating system, but today there are even specific operation are sysenter or then later syscall. Okay, as for the instruction set, there are more options how we can write instructions, the more notations how they can be written. Intel has started with some initial notation where assignment of the data transfer instruction, which is represented, for example, by move instruction, is from the right to the left. On the other hand, there is a history from the previous DETS processors and another systems which has been used with AT&T Unix, which has a rule to assign the value from left to the right. So be careful if you see a listing, and the listing which you get for the homework number 4 for the Intel variant is in this AT&T syntax, so it assigns from the left to the right. And in this case, the size in the Intel of the operation, if it is 8-bit, 16-bit, and so on, is given by the use of specific registers. So if you use AL, it is 8-bit. If it is some pointer where it is not possible to recite, then you need to write something like byte pattern and so on. So quite complex construct. On the other hand, in that AT syntax, you know directly from the last letter of the operation that this is a move byte, move word, but in this case word is considered that original 16-bit word of the 8086. Long is 32-bit and quad is quad word. So it is in the fact 8 bytes, and it is 64-bit to a destination. The registers in the Intel syntax are directly represented by a name of the register, and access to given address is represented as, for example, AX. This means the address at the AX register value. On the other hand, in the AT&T syntax, it is defined that the text without the prefix is in the fact address of the global variable, and for this reason there is the % sign used to distinguish the names of the registers from the labels. As for the immediate operand in the Intel syntax, it is plain number, or if the number ends with the H suffix, it is in hexadecimal. In the AT&T syntax, the immediate values start with this dollar character, and hexadecimal is written same way as in the C language. So basically this one is assignment of 32-bit value to the EBX register. In this case, it is the same in the Intel syntax, where the order is vice versa. If it is hexadecimal, then it has to start with some decimal digit, then you can have a hexadecimal value, and it has to end with the H. And because you can assign even from the shorter, narrower register to some wider, then in such case, you need to use the operation which does a sign extension or a 0 extension to the full width of the destination register. If we look at the access to the memory, then in the AT&T syntax, the memory access is denoted by the brackets. So this means that we access the location which is pointed by ECX register. This is the address pointed by EBX plus 3. So it is same notation as you know from the RISC-V. But in this case, the assignment is in this direction in all cases. In the RISC-V, if you remember, load word assigned from the address to the register, and store word assigned from the register to the address. So there is, okay, it is problem that each assembler has its own particularities. So anyway, then there is a complex addressing which is possible on x86. In the Intel syntax, you see that those brackets are used same as for the array. So this is array access. And in this case, you can specify that you want to use one register as a base, another register as a index, and it can be multiplied by a value 1, 2, 4, or 8. Or you can even add the base offset. So even 32-bit offset is possible to combine with this complex addressing. So addressing on the Intel is very, very complicated. To read it in this case, it means that it is offset minus 20 hexadecimal. Then this is EBX as the base, ECX, which is multiplied by this value 4. And this way you get the address to the memory. And why it is so complex? Because this complex addressing allows, in the fact, directly, for example, address the array of the structures. So if you have, for example, the array of points, then you have some array of points where in one word there is start of the array x, y for 0, x, y 1, and so on. And you can say in this case, EBX point to the start of the array. I want to use a given index. So for example, index 1. If it is point 0, this is point 1. So point 1. If the x and y are 32-bit, then you can multiply it by 8. This way you get with the address to the appropriate point. And then you can add even the offset, for example, that you want access not the X but Y. So you can add the 4 and so on. So it is really complex addressing, and it is possible to left out some of the components and use in the instruction, which even allows that complex addressing to use something simpler. And according to the combination of address and the modes and so on, some additional immediate values and some additional mode information is added into the instruction. So instruction is encoded by the sequence of 1 to today 15 bytes, which is quite complex. There are even a very complex instruction to allow a whole blocks operation. So there are a repeat prefix, for example, which allows to specify repeat the operation as many times as is specified in a ECX register. And if you provide the operation which should be processed, then that operation has implicit addressing, where there is a source index and destination index register, and operation is applied to the memory at those two locations. And then you specify, or that single instruction specify that we move to the next location in the memory, and it is possible to say if we want to iterate through the arrays from lower addresses to higher, so in this case we add the size, or if we select a negative direction -1, then we can iterate downwards. And so, that change is applied to both operand, and if you access, for example, locations in the memory as 32-bit, then those registers are advanced by 4. And then the ECX register is decremented, and if it is still not 0, then a new cycle of the execution of the operation appears. And there are those so-called string operations, because initially it was mainly for the text strings, which means move one string from one location to another, but do not check the final 0 character or something like that. CMPS compare to strings, loads and stores the values to some locations. Then there is possibility to do some scans and input and output, that you stream the whole block of the memory to a single port and so on. And you can combine this with the prefix rep, which means repeat ECX times, or you can even combine those operations with a repeat on equal or repeat on non-equal. And in this case, the operation stops on the first condition which appears. So basically, if it starts with, for example, you have compare string with the maximum length specified, that operation, str cmpn. So basically, directly this instruction can proceed something like that, that you repeat the comparison and stop at the first word or first byte which differs, or stop if there is no difference, and so on. So, and there is an example how you can copy or fill, in this case, fill whole array by a -1. So we have integer array, each location is 4 byte wide. So it is store double word, which double words in this case means a 32-bit value. You specify that the array, start of the array is set to the EDI register. Then you specify how many times we want to proceed the operation. then toss_the operation stores the value from EAX register. So you prepare the value in EAX register and then say, okay, repeat 128 times this special string operation, and you are done. So basically it is not necessary to load again and again the operation and decode it and so on, because it is done directly in the processor. If you want to find the end of the zero terminated string, then basically you start from some start. You can have some limit, because you know that the string, for example, cannot be longer than 128 bytes. And in this case, when you find the end, you break. And in this case, I informs how many bytes is the string in the fact shorter than 128 bytes. So it is easy that then you can compute the length as the actual 128 minus I, and you get the value. And it can be translated, okay, we specify the location of the string, maximum length of the string that we want to compare for the zero value. We said that we want to repeat on non-equal. So if it is not equal to the zero, then you can ask that the operation is repeat, which loads and scans for the given value. If you look at the arithmetic at logic operations and syntax, then we look at AT&T syntax in this case, and X is placeholder for the width of the operation. So it can be byte, word, 16-bit, 32-bit long, or quad word, which is 64-bit operation. And the instruction has only two operands which can be defined, so basically encode into the instruction. So one of those operands is the source, and the second operand is source 1 in the fact, and second operand is source 2, and even a destination. So basically you cannot add two values together and store the result to the different register, but you need to load the value to one register, to the second register, and then left the add operation to modify one of this register, which will hold the sum of those two registers. So this is the operation to add the 5 to the 64-bit RAX. This is operation with the 32-bit address, 64-bit start with the R, E is 32-bit extended register. So this means to take the value from the location in the memory. In the fact, -4 is some local variable on the stack, and add it to the EAX. Or you can subtract value of EAX directly from the local variable. So it is possible to directly modify a local variable which is not in the register. So basically you see that it is different from the pure RISC architecture, which has so-called load store principle, where only a load and store operation can access the memory, and the rest of the operation doesn't access memory at all and process the data only in the registers. And you can do addition, subtraction, you can do bitwise AND, OR, XOR. In the fact, it is quite often used for the fast clear of the register, because if you XOR a register with itself, then the result value is 0. There is a multiplication and division, which is quite complex. Initially, the x86 allows to multiply only the AX register with some another register value, and the result was directly put to the EDX AX. So basically it extends the size. Later, there has been added even the variants which allow to specify destination in the different register. But if you want, for example, to multiply two 64-bit numbers with 128-bit result, then you need to use this operation which result in with the value in R, dx and R, ex. AX, R, AX. Division, in the case of division, we can divide a 128-bit value with 64-bit value, and then in one of those registers we have a quotient, the result, and in the another one we have a remainder after the division. So one instruction can provide both results. And we can have a multiplication and division for the signed numbers and unsigned. So this is unsigned, and if it is integer, then it is signed multiplication and division. And there are even some single operand instructions. Okay, functions, instructions probably would be better word. For example, there is a specific operation to increment and decrement. But on the 64-bit variant, in the fact, those has been used for some special prefixes. So then there is a classical logical shift right, left, arithmetic shift right, and then there are even the operation to rotate the bits through the register. So basically, one option is that you have the carry flag, and you rotate the bits, for example, to the right, this way, and the least significant bit is copied even to the carry, or you can rotate through the carry. So in this case, if we put there the carry, then in the fact the carry is stored the value to the most significant bit, and least significant bit appears in the carry. So there are quite a lot of options for those operations. As for the control flow or branches and so on, then there are no combined instructions which can compare to registers and directly branch to some target. You first need to test, which is in the fact the operation end, which provides the information if the result is 0 or non-zero, and some other flags, and the compare operation, which provides a subtraction and stores the value into the Z flag, and the see if there is overflow and so on. So from those operations, you can follow with the conditional jumps, which can use those flags which has been set in the arithmetic logic unit. So you can have the jump target, which is unconditional. Okay, so it controls directly that you jump somewhere. Or you can jump only if the previous operation result in the 0. So in the fact, in the case of compare, that they have been equal. Or if the result specifies that the two values which has been compared are non-equal. Jump on grade or jump on above. So you can specify it is the jump at the case of the signed and unsigned comparison. So greater is unsigned, no, greater is signed, and above is unsigned. Yes, unsigned, it is correct. Or you can jump if it is bigger or equal, greater or equal, or above and equal. Or you can branch if it is less, where less is signed variant, or branch on below, which is unsigned variant. And below and equal, and branch or jump on the 0 result if 0 flag is set or not set, and even on the overflow. So you can test a lot of those information. For example, the testing of overflow on RISC-V is a little more complicated. Rest is probably, in most cases, the similar. Okay, so what do you think about the sizes of the code which is compiled for the complex instruction set and for some RISC-reduced instruction set architecture? So, C? Okay. It was the initial idea of complex instruction set processor was at the time when the fetching of the instruction was considerable amount of the time for the processor executing the instruction because the memory was slow. So the idea was that by the creating the complex instructions which can combine the access to the memory and operation and so on, that there will be less instruction necessary to read and so on. Yes, so you have.
Does it mean like if we are asked what program is longer, does it mean like in bytes?
Or in bytes, in this byte, okay.
So this is probably longer. So it's from some to 14 bytes.
But some of them are 1 byte. And in the RISC-V, you have much simpler instruction which cannot combine that offsetting and so on. So yes, it can seem that thanks to that complex addressing, which allows you to directly access a given location in some array of structures and so on, that it can be shorter. And it is questionable. So basically, for example, here, there we have attempt to increment 32-bit value in the local variable at the given location in the memory at some offset. So you see that on the in this case we get to the single instruction in the Intel syntax. And for the RISC-V, we need to first load the value, add the one, and then store it to the memory. And this operation is 32-bit encode, and this one is probably, in this case, I am not sure, it would be 32-bit as well. I think that it would be 32-bit as well, because it needs to store that offset. But it is single instruction, and there you need a 3 instruction. If you want to copy data from one location to another, the block, then you have seen that if we set up the correct way the registers, then we can use that single operation. And on RISC-V, we need to use this sequence, and this sequence even includes a loop. So this is a single instruction which copies a whole block, and there we need to process this long set of the instructions. So at the first look, it seems that the complex instruction set processor instruction allows to more dense encoding, which is usually right if you allow only a 32-bit encoding of the instructions, which is, for example, the case for the Apple M1 or for 64-bit ARM, which doesn't allow the alternative encoding of the instruction. At the time of 32-bit ARM, ARM added a 16-bit aliases for most common instructions, so you can switch to so-called thumb mode. And at the end, that 16-bit encoded instruction on the ARM usually led to the shorter code than the Intel encoding, that complex instruction set. On RISC-V, you can freely mix the 32-bit and 16-bit encoding of the instructions if the given implementation provides that compressed instruction set extension. And at the end, it is similar, or thanks to the higher number of the registers, it can be shorter. So it is, and it is much, much easier to execute because those instructions, those complex instructions are internally translated to the long sequence of the RISC-like instruction in the core. So, and usually, thanks to the higher number of the general purpose registers, you do not need to use the memory for local variables so often, and thanks to the better calling convention and so on, more modern calling conventions, I think that a RISC is usually a win. Okay, if you compare it with original CISC implementation, which processes the instruction in the multiple cycles with microcode and so on, then RISC is for speed is total win. Okay, but I should ask you here. So, what do you think about RISC and CISC in the speed? What is correct? It depends is correct answer. Yes. But another correct answer is D, because today every high performance architecture implementation uses the RISC-like style for the register naming and superscalar execution and pipelining. So in the fact there is no CISC processor internally today from those high performance, if you look at some, and small ones are ARMs anyway, or MIPS. So basically the CISC directly executed complex instruction set is okay, nonsense today. And okay, I would be fan of the RISC, so I would say that even the B is correct, that the RISC is faster. And if you compare the result of the ARM, I will have it in the next lecture, how ARM and mainly Apple has been able to grow the throughput of the processor, and how hard it is with the complex instruction set, then maybe you get some idea. Anyway, x86 provides directly the hardware to access the call stack and use the call stack directly by the instruction and so on. So we have seen that the RISC-V has the stack pointer or is using stack pointer. It is only the programmer's concept, but it allows to store the previous state of return address and so on, that basically you need to use it. But you can write a lot of functions which do not access, simple functions which do not access the memory at all. Those leaf node functions, that last functions which do not call something else. On the other hand, on the x86, we are forced to use the stack because the calling stores the return address on the stack, and they are dedicated instruction to manipulate with the stack. So it is dedicated stack pointer. It can be modified by standard arithmetic instructions. And before every push of data to the stack pointer is decremented, and we put the value to that location into the stack. On the other hand, if we want to do a pop, then the value is load from the address which is pointed by the stack, and then the stack is incremented. And you can store a 32-bit value, 64-bit value on the stack. You can even access a stack as 16-bit, and it is not suggested operation because you want to keep the stack aligned. And anyway, in the calling convention, there is a rule that stack has to be aligned, same as on the RISC-V. You can store even the state of the processor, that flux, at least conditional part of that register which is accessible to the user. You can even store a whole state of the user accessible registers on the stack and restore it back. And if you want to push some data to the stack, then the operation push is in the fact equivalent to subtraction of the stack pointer by the size of the operand, and then moving, for example, in this case, AAX to that address. On the other hand, if we want to do a pop, then we load the data from the stack top and then advance the stack, increment it by the size of the operand. If you want to do something like on the RISC-V, where you reserve the space on the stack and then you address a location on the stack, then it is not a pure stack computer. So basically, you can use the offset to the stack and access a different location in the memory. So there is a question, or do you think that is faster if we do those simple instructions without the offset and push the arguments, for example, or some registers on the stack, or if we first move the stack and then use the offset addressing against the stack? So which one of those two operations or sequences are faster, executed faster on the superscalar architecture? Which is interesting. This is for sure longer. Those will be 1 or 2 byte instructions. Those will be instructions which need the addressing. Yes. B. Yeah, B is faster. Yeah, okay. B is faster because in this case, those all instructions are interdependent. So basically, the modification of stack pointer is a dependency for the next instruction. So the instruction scheduler needs to wait till the previous instruction has modified a stack pointer and so on. So at the end, this what looks like the good idea at the start of the design of the processor doesn't work well, and usually today you do not find those push instruction in the code, or very little of them, because this is much faster that you move, and all those instruction has dependency, but only on that first instruction. So when we do the move, or with the stack pointer, the advance of the stack pointer, then at this moment we are done, and all other instructions can run in the parallel. Okay, now if we look at the calling in the 32-bit mode, and this is only part which is important for you, even for the exam, because we use for all other stuff, we use a RISC-V model, but you should know how looks the calling with the stack, and we cannot demonstrate it on the RISC-V because on this we use passing of the arguments in the registers. So be careful, it is important that in the 32-bit mode, all parameters of the function are stored on the stack, and even not only the arguments, but even the instruction, which is call instruction to call the function, in this case, is pushing the extended or RIP to the stack, and then jumps to the start address of the function. So basically, you do not need to take care about return address register, which can be modified in the function. So for this reason, if you want to call from one function another function, you need to manually store it to the stack and so on. You do not need to do that because the call automatically does it for you. But on the other hand, for each function, it stores the return address, and even the return from the instruction is equivalent to the pop AIP from the stack. So for 32-bit mode, and even for 64-bit mode, we use the call instruction which store a return address directly on the stack. And in 32-bit mode, all arguments to the function are passed through the stack. Return value of the function, the return result, is stored in EAX register. Then the registers which are used to as non-clock variable, which has to be preserved by the function to the return is this set. So you have EBP, EBX, ESE, and so on. So basically, number of registers which you can freely modify in the function is ECX and EDX. So you have very little of the registers which you can freely modify. Rest has to be restored to the previous state. And if we look for the examples how the stack frame is built, then basically we usually, if we use a stack frame, then the function prolog starts with the pushing the previous value of EBP to the stack. Then we remember the ESP value in EBP. In this case, EBP is in the fact equivalent to frame pointer on the RISC architectures. Then we can subtract some value. This way we reserve 12 bytes for local variables or to save the registers or to prepare the arguments to some calling. We can access local variables or that area which we have reserved on the stack relatively to that remembered value of the frame pointer or EBP. And the first argument is 8 bytes above the EBP, because on the EBP it points to the previous EBP. Then there is a return address, and then there are the arguments on the stack. And at the end of the function, we need to restore the stack pointer to the previous position. Then we restore the previous value of AEBP and use the return instruction. And there is even such macro instruction or fuse instruction, which is called a leave. And this is equivalent to those two combinations that it first restores stack and then restores the previous EBP value. So if we look how the actual call looks like, then there is a function which should, for example, add those 4 values. So we can use that non-optimal way to push the arguments onto the stack. We need to start from because we start with the stack somewhere here. So we do the push the last argument and so on. Then we push the first argument here. Then we invoke the call instruction. Call instruction pushes a return address onto the stack. And then in the function, in the prolog, we store the previous EBP value. So again, we subtract the 4. Then we push, for example, in this case, EBX to store the value because we want to modify that register. Then we can build there the space of 16 bytes for local variables. We can access local variables through the EBP minus something. In this case, it would go to EBX. But anyway, we can use those negative and positive EBP plus 8 to access the argument 1 plus 8 plus 12 to the next argument plus 16 and 20 and so on. So basically, we can access this way the arguments against the EBP. So this is the example how we can access the arguments. And the function epilogue usually use leave. So basically leave returns back the ESP to the previous EBP location, restores the EBP value, and returns to the caller. And this is quite inefficient because for each call in the 32-bit mode, you need to store all the arguments onto the stack. And this means a lot of manipulation with the memory, There is some forwarding that actually the changes do not need to reach the memory, that usually you can forward the ongoing push operation to the another addressing to the stack as a local variable or as argument and so on, but it is quite slow. So for this reason, in the 64-bit mode, the calling convention has been changed. There is different for the Windows and different for the ELF standard systems like BSD or Linux and so on. And in this case, up to 6 integer arguments are passed in the registers directly, and we have not only the 8, but we have 16 registers. So the rest of the registers is called R8, R9, and so on. And those 6 are specified that they can be used for the argument. And up to 8 floating point argument can be passed through the multimedia registers. And the rest of the argument has to be passed through the stack anyway. But usually the functions which has more than 8 arguments are not so common. So for a lot of functions, basically, you do not need to store arguments on the stack. There is one problem, that because you pass some arguments in the multimedia registers, some arguments in the integer registers, then if you have a variadic function or do not know how the function prototypes look like, then for this reason, it is necessary to set up AL, the 8-bit part of RAX register, which informs how many arguments has been passed through the multimedia registers. In another case, you are not able to do that iteration with variable arguments. So it again is a little complicated thing, but for the RISC-V, when you are using floating point registers to pass arguments, there are some troubles as well. Return value is returned in RAX if it is up to 64-bit. If it is 128-bit, then we can combine RAX and RRDX. But if it is longer, then we have there that hidden argument which points to the location where the result should be stored. There is a specification that those registers has to be preserved, so those are those non-clobberable, and the rest of the registers can be changed freely. And what is interesting, there is specified so-called red zone, which is 128 bytes below stack pointer, so area which usually is considered as non-preserve, which can be used for some signal handlers and so on the RISC architectures. Then in this case, it has to be reserved and skipped if some signal or some another more complex constructs are executed. This is for this reason that the addressing and offset with this small value are encoded as a shorter instruction, and for this reason they decide to do this specific thing. So the stack has multiple purposes. It stores the parameters for the function, current, which takes the caller's arguments from the stack, or it allows to prepare the arguments for the another call inside the function. In the 64-bit only if they exceed that 6 arguments which can be passed to the register. Stores the return address, which is pointer to the next instruction which should be executed after the call instruction when the called function is finished. And it can store local variables which are stored in the stack. Be careful that you should not use a stack for some very huge data structures. it is stack can be limited. Usually for the first thread in the application, it is not so much limited. It can extend. But you should check that the size of local variables is somehow reasonable. And if you program for the operating system kernel or some embedded system, you should be even more careful. And be careful that recursion call of the function can again exceed the stack. So there are some quizzes. So if we have this and this code, and we have there this I variable, which is in this case, it is before the it is a global variable, so it has to be, the space for it has to be allocated, or maybe it it has to be allocated into data section, or maybe BSS if it is not initialized. Maybe I should write there that can be even a BSS, because it is a global variable, so it is allocated by the compiler. And it has, fixed location, or today it is not fixed location, but a location which is randomized to prevent some attacks and so on. But it is directly encoded in the program code. Okay, or at least offset. If we look at y variable, so it is this variable inside the factorial, so it is a local variable in this case. So it no, because we do not want to call a malloc or something like that. So it is a. On the Intel, it is more probable that it will be on the stack. In the case of RISC-V, it could be probably in some. But it is overwritten by the factorial function, so it can be kept even only in the registers, because you use it only there. Bigger problem is with the x variable. What is the problem with x variable? That we use x variable. So y can be, even on Intel, it can be only in the register. For the x, it is argument, which is used on multiple places. If it is the 32-bit Intel, then it has to start to be on the stack, because the arguments are passed over the stack. If it is 64-bit, that it can be passed in the register, but there is a problem that when we call the factorial, it will be overwritten in the register. So we need to store it to some safe register or onto the stack. And if we store it into the safe register, then the safe register has been before that stored onto the stack. So in this case, it is in the 64-bit case in the register, and then on the stack for 32-bit case, it is this one for sure, almost for sure. For 64-bit, we can have a discussion. So basically, you see that it is not so easy to specify sometimes, because but it is without the optimization. So basically, then it is probably on the stack in such case. But on the RISC-V, it has to be passed in the register, because it is the rule. Where is stored return? I have there a mistake. Address. So return address, that address to which instruction we should return. In this case, it is It is this one, because in RISC-V it is in the register, but because we call the function, it has to go to the stack. On x86 it is directly on the stack thanks to the call instruction which store it onto the stack. Okay. There is a quite problem that the assembler is quite complex because you have multiple variants how you can set the value. So for example, you can do this move to set the ESE to some value, and you can do it by those two operations, for example, and in some cases it can be shorter than if you do it directly because of some irregularities in the encoding. Then, for example, this is typical way how to clear the register, that you XOR it with its own value, because in this case you need to encode the immediate value, which you do not want to encode because this is longer instruction. And then there is one instruction which is quite complex, because as you have seen, we do not have any 3-operand instruction for the integer arithmetic in the Intel. And if you want to add two values together, but want to store the result in third register, that you do not modify any of those input registers, which is sometimes the case that you want to reuse those values later, then in this case you do not have the 3-operand addition. But for the reason that you can compute effective address, so address to some that complex indexed position in some data structures and so on, but you want to remember it and reuse it for the another access to the memory, then there is that specific instruction which is called load effective address. And that load effective address allows to use that full complexity of the address calculation with all those 4 components and store the result in the register. So in this case, for example, you can say that this operation is same as we subtract the 12 from the ESP. In this case, it is not a big win to use this operation. But if you, for example, want to add one value, another value multiplied by 2, and add some immediate value, then you can combine all this to the single load effective address operation and use this complex instruction. It is interesting that for some implementation, this load effective address is computed on the load store unit, so it can be computed in parallel with another arithmetic logic operation, so it can enhance the throughput. On the other hand, on some Intel low power or rank implementation, it is much slower than the computing this with the arithmetic logic instructions. Then if you want to work with floating point arithmetic, then there is some coprocessor, and Intel has been quite good in the floating point arithmetic implementation in the hardware from the beginning. So they have implemented 8087 coprocessor in the 80s. And it supports a single 32-bit, double 64-bit, and extended 80-bit format, as well as some exotic, but they are not important. But those are that standard formats, and that coprocessor contains even 8 registers, which each is 80 bits wide. And what is interesting, and I think that it is quite unfortunate, is that those registers are organized as a stack. So when you store the value to those registers, then you advance some pointer in that cycle, but that stack has only a depth of the 8. So, but even that you can use those operation with implicit operands on the stack, you can even access a location directly on the stack, relative to the top of the stack, so you can combine both of those methods how to access the values. And usually those operations, the basic mode is that they work and combine two values on the top of the stack, and then pop one of those operations and store the result onto the stack. So it is, from 486, this coprocessor is directly on the same die, so it is single chip solution. And we have there a lot of IEEE 7 and 54 standard conforming operations. And if we go to the operations, then we can have there a load store operation. So all those operations start with F, which means that it is floating point unit. And FLD is load the value from some location into memory and push it onto the stack in the coprocessor. FST is store the top of the stack to some location in the memory, but it is without the pop, or you can use FSTP, which pops the value from the top of the stack and stores to the memory. It is possible even to load and convert integer values from the memory onto the floating point registers, but there is a conversion, so it is not stored as the integer value, but it is converted to the floating point. It is possible to store the integer register, store the integer value from the register, so basically truncated floating point value converted to the integer to the memory, or it is possible to request that it is stored with the routing and so on. So you have all those operations. There is a list of the arithmetic operations. Usually in the simplest form, they operate between the stack top and the one value below the stack top, so it is ST1. But you can even specify that it operates on some offset and stores the result somewhere into the stack. So there is a floating point addition for the float and double operands, and store the result at the top of the stack, or you can do the integer addition from the memory to the top of the stack and store the result into the stack and so on. Add one to some location into the stack and so on. So those are all the combination of add operation which allows this lot of different options. Probably the fastest is to add the top of the stack to the location in the fact below the top of the stack, and then delete the top of the stack. So it is classical add two values on top of the stack, take them away and store the result on the stack. For subtraction, there are different options, and you have there even the reverse option where you subtract the STI minus ST0 and so on. So you have those two options. Then there is a lot of the another functions, goniometric and so on. So basically you can compute the sine and cosine value and store it onto the top of the stack, replace the top of the stack with the new value. It is possible to do a different kind of multiplication by the power of 2. It is possible even to compute arcus tangent and so on. There are even some operation which allows to load some predefined values onto the stack, onto this internal stack, not the memory stack, that stack in the floating point register very quickly. So there is an example how to compute this expression and store the result somewhere. So first we require, okay, we want to loads this value. We do a multiplication of the top of the stack with this value in the memory. We can load the third operand, so it is that 3.3. We compute the sign operation. We do the add with the pop from the top of the stack. So now on the stack we have only that result of the addition, and we store the result to the memory and do the pop at the end. So basically we have returned the stack onto the same location as has been at the start of the expression computation. If we compare it with RISC-V, that it has a float, single, and D double extension, it adds additional 32-bit internal registers. If it is only that F variant, that it is only a 32-bit wide. If it is with a D or both, then it is 64-bit registers files, the floating point register files. To load, you have standard floating point load word, store word, load double, store double, and so on. You have there the different floating point add and subtract multiply operation, which directly specifies registers which should be used. And the S means at the end that it is single, D it means a double precision. And you can compute square root, and what is important, you can compute even some multiply and addition or accumulate instructions, which are very important for the convolution computation and for the multimedia and so on. But anyway, if you want to process some complex multimedia stuff, you probably want to work with vector instructions, which is another level which we mostly skip there. Anyway, you can compute minimum and so on. And there are the convergence function and so on. But anyway, at the moment when you want to process a multimedia data or do some wide computation on the matrices and so on, then you want to have some single instruction, multiple data operations. This is again for the exam. You should know that there exists some set of the instructions where you have single instruction which operates on the multiple data with the same operation. And it can, the initial version was multimedia extensions which reuse x87, those 80-bit registers in the x87 floating point unit. But it doesn't use it as a floating point, but as a 64-bit integer registers. Disadvantage of this mode is that you need to switch the processor from one mode to another, and in the MMX mode you can work with those integer values stored into the floating point registers. Why it is done this way is for that reason that operating systems has know how to store the state of those floating point registers when they switch from one task to another. So they decide that because at that time it was a big problem to convince Microsoft and others to modify the operating system when the compatibility is not kept and so on. So for that reason they decide that they will reuse the registers which are already stored by the operating system. And what it allows, if you have 64-bit register, then you can place 8-byte values into it, or 4 16-bit values, or 2 32-bit values. And then you can do the operations in the parallel. So you can do the addition, subtraction, and so on, for example, multiple pixels by the single instruction. We will see some examples. So for example, you can add the vectors. If you will use a homogeneous system of the 3D space vectors, if you know it, it is used in the games and so on. That basically you have x, y, z, and the 1. And those vectors can be used for all perspective transformation, because this one at the end allows you even the shifts, because if you have then matrix which is 4 by 4, then with this setup basically you can do all the perspective operations, rotations and so on, very simple way. And if the 16-bit representation of the coordinates is enough in this case, then you can, for example, do those operations, the addition of two such vectors directly. Okay, there you will have some problems with that one. Oh, okay, but anyway. And you can decide if it is that packet word addition with the overflow. So in this case, if we add those two unsigned values, then you see that there is overflow. So basically we get, in the fact it is -1, even that we attempted to add a 2. For example, if you want to change the intensity of some point and there is overflow, then you will have a black point in the middle of the screen and you do not want it. So for this reason, there is even the option to use saturated, limited addition, which ensures that if you add the values and the result would overflow, then the maximum or minimum value is kept in the memory. And it is for the signed and unsigned arithmetic. Then you can do this packet multiply, so basically and addition. So in this case, in the fact there should be a multiplication sign. That is, but there is more such operations that basically you take the corresponding values, do the multiplication with those two, take the result, but because the multiplication widens the value, that it, if you multiply two 16-bit values, you can get up to 32-bit value. Then because it could overflow, and you quite often need that scalar products of the vectors, then for this reason they decide that if you do those two multiplications in the parallel, that basically those results will be combined into the partial sum. So you can do something like this. Or the other option is that you can multiply but and keep all the 4 results, but keep only low part of the result. In this case, if there is a saturation, you have problems. But you can keep even upper part. So basically, the result of multiplication divided by, in this case, 64,000 and something. 64,000, okay. And this way you can combine the multiplication. So there is an example if you have masking of the image in image. So basically, this allows to use, for example, background and some reporter, which is filmed before a green screen. And if the mask, in this case, for example, if the image matches, or in this case, if the mask is 0, then it allows to decide that the green screen should be replaced by the background image. And you do not need to do this in the for cycle by the if, but you can say, okay, I want to specify and compare the masking value with all, in this case, 8 pixels, if they are represented by 8-bit value. So you can do a parallel packet comparison. You find which of them are green. For those green, you can get the information that the masking comparison sets each location to the zeros or to FF if there is equality with the green, and then you can use those masks. So at the end, you do not need to do any conditional execution. You only use the masking, and this masking allows to combine two images together. All this MMX is for the integer. Then AMD came with 3 now because they found that they would like to work with those floating point values, but in the parallel manner. And the first they tried to attempt to reuse floating point registers, but later Intel came and decided that they will add a new set of the register. And it is streaming single instruction multiple data extension. That streaming is from the multimedia and for the video processing and so on. But in the fact, those instructions can be used for the fast matrix computation, for artificial intelligence, maybe for some complex computation and so on. And they have added at that time a new set of the registers, where each of those registers is 128-bit wide, which allows to store 4 floating point values. And we have seen that homogeneous coordinate system in 3D needs those 4. So basically it maps quite nicely to the game geometry and so on. And okay, for floating point with double format, you can store only the 2 in the single 128-bit register. And for those registers, there has been added operation not only to do that packet operation, but even to apply to it the scalar operation. So at the end, today, 64-bit code usually doesn't use floating point unit, that original floating point unit with stack and so on, those problems at all, but all is done in those SSE registers. And there are operations to move data from the memory to the register, to do the addition, subtraction, and so on. You can specify if it is in the integer or double or single representation. You can use even the logic operation on the representation. So those logic operation together with masking allows even to clear some floating point values and combine them and so on. And there are those scalar and so those packet operations. So for the packet operation, you can use something that you process a whole registers, or you can specify that you want to process only the operations scalar on the lowest bits of the register. And the evolution is that with this SSE2, 144 new instruction has been added, then 13 instructions, 16, 170. So basically you see how the instruction set is getting complex and more complex and so on. Then the encoding has been full, so they have added the prefix for AVX, advanced vector extensions, and AVX2 adds 256 bits registers, but in the fact those registers are the extension of the original XMM registers. So lower part is XMM and upper 128 bits has been added. Then maybe you know that there is AVX 512. There are problems that Intel on some those hybrid architectures where there are powerful cores and efficiency cores has disabled it later with the microcode because the efficiency code has not executed the 512-bit operations, and it was quite complex for operating system to decide which task should run on which processor and so on. Today they have switched again to AVX, I think that it is 10 or something like that, which defines that the 512-bit operations are mandatory. Then architecture from AMD provides these wide operations on all their implementation, but on the other hand, sometimes those very wide operations are not as fast, or for sure they are not 2 times faster than the 256-bit operations, because there is a limit throughput to the memory, and on some implementations they have only narrower implementation of arithmetic logic unit, that vector arithmetic logic unit. So basically, if you schedule well shorter instructions, which then maybe sometimes you get a better result. So basically, it is a topic for a lot of research, optimizations, and so on. So we have done a quick overview of x86 architecture. It is a topic if you want to find how the protected mode works and how to start operating system in it and so on. It is getting really, really very complex. There is a stored presentation of Professor Gurevich from Israel on our pages, which he has been part of the Intel engineering team in Israel, because some Intel cores has been developed there. So you can go in the depth into the history, for example, there, and it is really, really complex. So for the exam, it is important to know that there is x86, that there are some on x86 or other architectures, single instruction, multiple data operations to speed up the processing, and the critical is to know that specific stack-based calling convention, because it is something which was original calling convention even for a lot of other architectures, and anyway it is partially reused even in the RISC architectures, where the arguments do not fit into the registers, because you cannot have infinite number of the registers. Okay, so it is all for today. Thanks for your attention.